So it's just showing you the power of first order logic, how epsilon delta proofs are common in calculus sort of thing, in which in general, if two people are kind of fighting over resources, right? The programmer wants longer and longer code because then he can have more detailed algorithms, and the input wants to be a bad input, so it can be big, and it's all about who gets to go first, right? So in the converging, we want to say that it's converging, it's going really close, and the adversary can say how close we want, and then we got to say, well, how far out you go, right? So we've seen this already. So it converges to some constant C, right? If there exists a C in which it converges to, right? It gets closer and closer to C. In this case, it's converging to 0. And so how do we measure how close it is, right? For a given value of F, we just see how close this distance is, right? And then, well, for which epsilon, how close do we need it to be? Well, we want the adversary to be able to say how close. The adversary can go as close as they want. It has to be bigger than 0. You can't say 0. You can't say, I need the exact value, because here we're never going to get 0, right? And then for which n, well, you need to get that close, and then you have to stay that close forever. From then on, you have to get closer, right? And then you could say, well, which definition of big, right? And here's the key game, is that the adversary can give me as small of an epsilon as he wants, but then I get to say, you have to go really far out, right? So this is kind of the proof that this converges. And we were using the idea that if you don't quite, here I have to come up with the n naught, but I don't really know what value to come up with. So I wait, and then when I see this, I say, oh, that's how far I go out, right? Everybody kind of gets this example? All right, so I don't know, I threw this on. Hopefully it didn't kill too many people. How many people feel they got it? How many people feel they didn't get it? How many people are nervous? All right, well, let me first say that I've had plenty of tests. In fact, for the third year algorithm course, I would have 5 tests every term, and half the people would get 0 in each one, right? And the key is we need to tell you what's expected of you, and you know, you can see, what I want you to see is that if you play the game, it works, but you have to trust to learn the game and to figure out what's going on, right? All right, so here's our sequence. It alternates between 1 and -1, right? So the prover here needs to prove this statement. The prover is asked to prove that the sequence converges, right? But he says it doesn't converge, right? It bounces back to between 2 values. It never gets closer and closer. So hopefully people can, we talked about it actually during the test, right? So if it doesn't converge, then we have to negate the statement, all right? And I was looking over people's shoulder, and they were bringing it in one line at a time. I certainly wouldn't do that. I would just copy each one down, switching the Forall to an exist, right? And it doesn't, remember, it doesn't change. We're talking about epsilon's bigger than 0, right? So that doesn't change. We're talking about n bigger than n naught, so that doesn't change. And then we bring the negation all the way in here. So everybody able to do that? Right. And really, you can see blue goes to red and red goes to blue. So what we're doing is we're switching the roles, right? So now the adversary is to try to prove that it converges. But our goal is to prove that the adversary loses, right? That's the nature of our beast. All right, so if the adversary would play the game, now the adversary is claiming it converges, all right? So I say to the adversary, it converges to what? If you try to prove it converges, tell me where it converges. All right, so the adversary gives me some C, and let's just practice, right? We don't know what he's going to give us, but we can practice. If the adversary set C equals 1, then what do we say? Does it converge to 1? No, we look at, for all odd n, I don't care how far out you go. For all odd n, where the distance between 1 and -1 is 2, right? So we don't get close at all. So maybe the adversary tries again. What happens if I say it converges to 0? And that's, at least it's sort of balanced. In some ways, 0 feels like a good answer, right? But we can notice for every point, you're 1 away from it, right? So we're never going to get this inner thing as long as we make epsilon less than 1, right? Everybody kind of following this, right? So we'll try one more time. He says, well, what happens -0.5, right? Well, then we compare it. Then we say, well, for all even n, even if they're as big as you want, even n, you're going to get 1. And the distance between 1 and -0.5, right? It's bigger than 1, right? Because you get the 1 down to 0 and then a negative piece, right? Are people following this? All right, so what do I want you to be able to do? It'd be nice if you could get intuition about these statements, and we're spending lots and lots of time giving intuition, right? If you looked at the review slide, it was pretty short, right? And what was all the rest? It was just me banging at how can I give you as much intuition as possible. All right, but suppose we don't have any intuition. We just play the game. It says for all C. All right, so the adversary gives me an arbitrary C, and my goal now is to prove that it doesn't converge to C, right? And as we've kind of seen, and I gave you this hint in class, in the test, there are kind of two cases. So the two cases are, do I defeat the adversary by giving him a 1 or by giving him a -1, right? And it depends on whether his C is closer to 1 or closer to -1, right? So I'm just saying, let's split the cases as to whether the C he gives me is positive or negative, right? And so then we could prove, how do you do that with purple table, right? We assume that the C he gives us is negative, we go up and prove. We assume that it's positive, we go up and prove, right? In this case, I told you don't do both cases, because if you can do one, you can do the other, right? They're pretty similar, right? All right, so we're assuming that it's negative. All right, so now I have to come up with an epsilon, and on the test I said, hey, some of my, the hardest part coming up with these proofs is when you have to construct a value, right? What value to construct? And Otherwise, you just brute force it, right? You just do it. And, I gave the hint that I like a third and I like even numbers, right? So now what do I say? Well, let it be a third. And why did I make it a third on the test? It was before I was just banging it out. And one would have, in our cases, it feels like one was good enough, but I sort of thought maybe there's a half in there and I want to make it smaller. Anyway, it shows you that epsilon's small anyway. You can make it whatever you want, right? So the adversary is giving me some C, and I'm saying you can't converge within it. You can't stay within a third of this function because it's flipping around, right? So then we come over here to Forall. Now after I give the adversary my epsilon, right? The adversary gets to define how far out to go, right? Gives me the n naught. And so we just say, it says Forall n naught, so let n naught be arbitrary, right? You can go out as far as you want, right? Then what am I supposed to do? I'm supposed to construct an n, right? And what properties do I need of my n? I need it to be bigger than n naught. And my goal is to get f of n to be 1, right? Because it's far away from this negative c. So I make it an integer. Now, I didn't say that here, but one sort of lemma that we're using here is that for every n naught, there exists an n that's bigger than n naught, and that's even, right? And that's something, I sort of say we can sort of throw algebraic things under windows sometimes. Everybody say this is how I construct it. You give me a billion, I'll say, oh, well, billion's even. You give me a billion and one, okay, oh, let's go for a billion and two because it's even, right? All right, and then we just have to bang it out, right? We write down left side, right side, right? Here we want to prove that this difference is bigger than a third, which is epsilon. And well, for even n, we have 1 here, and the c we were given was negative. So the distance, I mean, people might get a little worded out with minus a negative, right? It becomes a positive. But, the intuition that a negative number is far away from 1, right? It's at least a third away. Right, everybody good? And that was it. All right. Any questions about that? All right. Proof by contradiction is what we're at next. And you heard me say that I don't like proof by contradiction, but it is used, and it's used in some good ways. And what I'm going to kind of argue here is that you don't really need to do it at all if you play this game the way this adversary game, right? So we're going to go over some classic proof by contradiction. You might have seen them already in 1090 because I think we were supposed to teach it. But we'll just review it. So what we're now doing is thinking how we can convert that into a game. All right. So a contradiction, of course, is a statement that's false in every universe, right? What's proof by contradiction is you prove that, right, you assume that you're trying to prove alpha. So you assume alpha is not true. And from that, you prove a contradiction. And then you say, well, how did I get a contradiction? Well, I assumed something and I shouldn't have assumed. So then we can conclude the opposite. Right? Everybody know proof by contradiction? And the reason I fight against it isn't really what we're doing here. Right? Here I'm showing you a reasonable proof by contradiction and a reasonable translation over to this game. But the reason I hate it is because people do it, but students do it when they shouldn't, right? When it's just not gaining anything. When you're doing purple table things, I've never seen a purple table proof that needed proof by contradiction, right? Right? This is, everybody get this? All right. So we've seen this before. This just proves that it proves that proof of contradiction works, right? You can turn it around. All right, and right. All right, so when is it useful? Is when I want to prove when I assume something. If I assume it exists, then I can ask the adversary to give it to me, right? So yeah, when this assumption of not alpha allows me to construct the existence of something, then that's kind of useful, right? All right, so here's a proof by contradiction. All right, we want to prove that every boy loves, right? So by way of contradiction, assume it's not the case, and hence we're assuming that there exists a boy who doesn't love, right? And hence now the oracle is assuring us that somebody doesn't love. So we can say, let B exist, be the boy that is, assumed not to love. And then we look at that boy and we see, well, actually he does love. And that's a contradiction, right? And so our assumption was false. And we've proved that all boys love. Right, everybody, this is the classic proof by contradiction that people do. All right, everybody get that? Now, I'm just saying, how does it translate over to the game? And if anything, maybe this will help reinforce what the game is doing, right? So what are we doing? I'm trying to prove for all B. So how do I prove for all B? Right? I let B be an arbitrary boy, right? Which is kind of, we skip all of this, and now we have some B, right? Now over here, I probably would have done B for all, but my point was to emphasize it's the same B, right? It comes from somewhere. We don't know what it is, right? This came from it came from our oracle, who assured us that something existed, but we don't know what she's giving us. Here it's coming from our adversary, right? And then we say, hey, look at this, in fact, B loves. And so we conclude that we have a for all, right? Everybody see this? So it's the same game. Any questions? All right. So let's just give some classic example. The Greeks were all about integers and fractions. They're called rationals, right? They didn't know about decimal expansions, right? All they were doing was fractions. So then they were trying to say, can we express square root of 2 as a fraction? Did everybody cover this in 1090? Anybody not cover it? Not cover it? You covered it? All right. Right. We want to show that you can't express it as a fraction, right? So how do you do proof by contradiction? You assume by way of contradiction that it is rational, and hence there's some way to represent it as a fraction, right? So here I'm saying if it's irrational, then it's n over d for some integers, right? And so then I can rearrange this to be of this form, right? And then somehow we'll prove that that's a contradiction, right? And so our assumption was false, right? And here, what are we doing here? I'd say it's really good to write down the first sort of statement that you're trying to prove, right? We're trying, and sometimes, how do I write down that something is not rational, right? That might be hard. So let's write down, what does it mean to be rational, right? We look up at our definitions and we say, what's the definition of rational? It's rational if there exist integers which make it into a fraction, right? And we're trying to prove that it's irrational, right? So for all n and d, you don't get square root of 2, right? And so you play it by the game. Let n and d be arbitrary numbers. We rearrange it, and so then here we're trying to prove for all n and d, this fraction doesn't give you r, right? And that's what we're doing here. We're proving that it doesn't, that they're not equal, right? Everybody see that? So the standard proof, I guess the Greeks used, is different than what I like more. I think it gives me more intuition. All right. So I'm trying to prove that for every integer d and every integer n, this is not true, right? And one way I can think about is what are the divisors of a number, right? I don't know if you know the prime number theorem. It says any integer 12 can be broken into 2 times 2 times 3, right? So we're going to ask, give me a number, and I'm going to ask, how many times does 2 divide into it, right? And I keep dividing 2 in it until it gets odd. And then I see, oh, 96 has 5 2s in it, right? Everybody get that? And then what do we know about this? The next number here, it's odd. Right? Everybody see how you can do this? All right. So now, if D has A 2s, right? If I square D, how many 2s does it have? Right? People see we double the number of 2s. Right? We have 5 2s here, and then we multiply it by 96, and that gives us another 5 2s. Now we have 10 2s. Right? Everybody see that? All right. So now we want to look at this equation here, right? If we multiply d squared by 2, that gives us one more 2, right? So now we have an odd number of 2s on the left-hand side, right? You can just see d squared is going to give us an even number of 2s, and this extra 2 gives us an odd number of 2s, right? Now you come over here, and what we have is an even number of 2s. So that tells us they can't be equal, right? Everybody kind of buy that? One picture I like is, say we want the GCD of 12 and 8, say, right? So 12 has 2, 2, 3 in it, right? And what does 8 have? 8 has 2, 2, 2. So you kind of take the intersection, right? And this becomes the greatest common divisor. People kind of okay with this? Right? Let's do another one. The Greeks, yeah.
Greatest common divisor. Is it supposed to be 4?
4? Yeah, it is 4, which is 2 times 2. Right? These are the primes that are common to both.
Yeah, I also have another question. So what is the difference between proving using contradiction and proving using negation? How are there, what's the difference between them?
Between my game and proof by contradiction? Nothing. Nothing. Except in this class, you know I like the game, so you should do the game. Right? And why are we doing this? Just to understand both of them better, right? This is helping us understand proof by contradiction better, helping us prove the game, understanding the game better, because we're seeing they're the same. All right, so let's do another one of these. There seem to be a lot of prime numbers, right? Prime numbers, nothing divides into it except 1 in itself, right? How do you prove there's an infinite number of primes? So you might have seen this proof by contradiction. Let's assume that the number of primes is finite, right? And hence, there's a maximum prime p, right? If there's a finite number of them and they're integers, then there's a maximum, right? So we construct, and then somehow we construct a bigger prime, right? Which gives us it contradicts it being the biggest, in which case we have our right, the number is infinite. Right, everybody kind of follow that proof? So here, I do recommend really writing it down is a first order logic statement. I mean, why are you doing that is because if I just say, hey, prove the number of primes is finite, right? You might not know where to go, right? But I'm saying if you write it down in this logic way and then play the game, it'll help you know how to do it, right? So a set is finite, right? If and only if it has a maximum p, right? So this is sort of in some ways, it's the definition of a set of integers being finite, right? So we're stating that there exists a p that's in our set such that everybody else in the set is smaller or equal, right? Everybody see this definition? Right? You getting this? It's just saying there exists a max that's bigger than everybody else, right? All right, so we want to prove that the set is infinite, right? And so we're taking negation. And how do you take the negation? Well, the exist turns to a Forall, the Forall turns to exist, and we negate the inner, right? So what are we trying to prove? We're trying to prove that for every p, there exists a bigger guy in the set, right? That's what the game gives me. It gives me, you give me a p, I'll give you a prime bigger, right? So that's exactly what we're doing here, right? So let p be an arbitrary prime number, right? It says for all prime numbers, you give me an arbitrary prime number, I can construct a prime that's bigger, right? And so then we're done, right? Everybody see it's the same. And as I'll repeat, in this class you do this, and in your life you can do whichever one gets you through the night, right? But my prediction this one, here I'm going to make just something up. It's all aesthetics, right? I might agree that this proof is more aesthetic than this if you're not really up on the game, right? But I claim you would figure out how to do it yourself better if you did it this way, right? If you're coming up with your own proofs. All right, anyway, how do we do it, right? We want to prove that there's a prime Q bigger than P. And so what do? We compute the factorial of P, right? Factorial is P times P minus 1 times P minus 2 all the way down. And then we add 1 to it. All right? So this is a really big number. And then every integer can be uniquely factored into primes, right? So we want to know what are the prime factors of this number, right? So we ask, is P a prime factor, right? We started with P, right? We were given P. So is P a prime factor of N? Does P divide into N evenly? Right? See, P divides into the P factorial evenly, but then there's a remainder of 1, right? Everybody see that? All right, so here, let's do it again. I gave you P, you come up with this big number N. And you can state P does not divide, right? What is, right? N divided by P, what's the remainder? And you'll see, well, P goes into this P factorial, right? It's sitting right there. Goes into P factorial. So if I divide this by P and I ask for the remainder is going to be 1, right? Well, the same for P minus 2, right? P minus 2 divides into this evenly, and then you get a remainder of 1, right? In fact, it's the same. Every integer smaller than P doesn't divide into this, right? So N must have, I'm not claiming M is prime, though it might be, right? But its smallest prime factor is bigger than P. And hence, there's some prime that's bigger than P, right? We played the game. You gave me a P. Did I construct it? Well, I sort of constructed. I took this and I said, give me any prime factor of this guy here. It's a prime, and this argument proves that it's bigger than P. All right, everybody good? All right.